Hello and welcome to this brief presentation relating to calculating areas of compound shapes. Typical shapes that we'll be analysing in this presentation are shown here. Each of the compound shapes considered in this presentation will be broken down into discrete rectangular sections. Then calculating the areas of the individual rectangles, we will calculate the total area of the compound shape. So question 1a, which is broken into 6 individual parts. We're asked to calculate the areas of the sections shown shaded below. Note that all the dimensions will be in millimetres. Part 1 of question 1, we have to find the shaded area of the T section, and in part 2 we have to find the shaded area of this box section shown here. The geometry is given as shown. What we need to do is consider breaking each of the sections down into their appropriate rectangles. So considering section 1, I would suggest a rectangle here for the top flange and a rectangle here for the web. I'd encourage you to stop the presentation and attempt question 1a parts 1 and 2 here, but the full solutions are shown on the following slides. So question 1a, here's the solution to part 1. Notice I've calculated this dimension here of 7.5 millimeters for the thickness of the top flange from the geometry given. So now I can calculate the area of the top flange. It will be 45 millimeters multiplied by my 7.5 millimeters, and then calculating the area of the web shown in green here, that will be 15 millimeters multiplied by its length, which is 57.5 millimeters. Evaluating the area of the T section is 1200 millimeters squared. And from our previous presentation, to convert from millimeter squared to meter squared, remember we have to divide by 1,000,000. So 1200 millimeters squared is actually 1200 times 10 to the negative 6 meters squared. Or of course we could write that as 1.2 times 10 to the negative 3 meters squared. Question 1a, here's part 2 solution. Calculate the area of this rectangular hollow section. I basically calculated the area of one outside rectangle and subtracted the inner rectangle to calculate the net area, or the area of the rectangular hollow section. So calculations, outside rectangle is 32.5 millimeters by 27.5 millimeters shown here, and I subtract from that the inside rectangle, which is 27.5 millimeters multiplied by 22.5 millimeters, and that's shown here. On the next line I simply factorised on the 27.5, which is common to both terms. Evaluating the area of the rectangular hollow section is 275 millimeters squared. And again for reference, just stating the area in terms of meters squared. This is question 1a part 2 with an alternative solution shown here. Basically this analysis considers the rectangular hollow section wall in terms of 4 rectangles. So here's the top and the bottom of the rectangular hollow section. Calculated here, 32.5 millimeters multiplied by 2.5 wall thickness. The wall thickness is constant for the rectangular hollow section, and of course there's 2 of these, top and bottom. Next I've calculated the sides here, 2 vertical rectangles. They're 22.5 millimeters by 2.5 millimeters, and of course again 2 of them. So evaluating the area again is 275 millimeters squared. Just an alternative approach there for calculating the cross-sectional area. Question 1a, here's parts 3 and 4 for you to consider. Again we have to calculate the cross-sectional area shown shaded of these two sections. The left-hand one is termed an unsymmetrical eye section because the top flange and the bottom flange are different sizes. And item 4 is an angle section, but it's an unequal angle section because the two flanges are different lengths and different thicknesses. Again, all dimensions stated are in millimeters. I'd encourage you to stop the presentation and attempt these questions, but the full solutions are shown on the following slides. Question 1a, which is part 3 solution. Our unsymmetrical eye section been broken down into 3 rectangles. The upper flange here, 12 millimeters by 3.5 millimeters. The lower flange here, which is 24 millimeters by 5 millimeters. And then the web, which is 39 millimeters by 2.5 millimeters. Evaluating the area of the unsymmetrical eye section is 259.5 millimeters squared. And stating the answer in terms of meters squared here. In question 1a, part 4 solution. Here's our unsymmetrical angle section or unsymmetrical L section, then broken down into 2 rectangles. First rectangle shown here is 4.5 millimeters by 56 millimeters, calculated here. And our second rectangle is 43.5 millimeters multiplied by 12 millimeters, shown here. Again, be careful how we've worked out the 43.5. It's 48 minus 4.5. Evaluating the area of the unsymmetrical angle section or L section is 774 millimeters squared. This is question 1a part 4, but an alternative solution. I've just broken my rectangles down into slightly different configurations here. So this time I have 4.5 millimeters multiplied by 44 millimeters for this vertical rectangle, and at the bottom here I have 48 multiplied by 12 millimeters for the area of this rectangle. Evaluating for area, that's still the same value of 774 millimeters squared. It's question 1a, part 5. We have an unsymmetrical C section, and part 6 we have a H section. Again, we've got to calculate all the areas that are shown shaded, and note that all the geometry is in terms of millimeters. I would encourage you to stop the presentation and attempt these questions, but I'll show you the full solutions on the following slides. Question 1a, part 5, here's the solution. Broken the C section into 3 rectangles as shown. First rectangle shown here is 25 millimeters by 5 millimeters, calculated here. Second rectangle shown here is 7.5 millimeters multiplied by 40 millimeters, shown here. And the final rectangle shown here, 50 millimeters multiplied by 12.5 millimeters, shown here. Evaluating the area of this unsymmetrical C section is 1050 millimeters squared. Again, just notice how we've calculated some of these dimensions. 25 millimeters here is 32.5 millimeters minus 7.5, and of course the 50 millimeters here is the 57.5 minus 7.5. And again, just for reference, dividing by 10 to the power of 6, the area can be written as 1.05 times 10 to the negative 3 meters squared. Here's question 1a, part 5 alternative solution. I've broken my C section into a different set of rectangles, still 3 of them, but the geometry is slightly different. I'll let you work through the solution at your own pace here, where you'll find that the area is exactly the same as on the previous calculation. And question 1a, part 6, solution. This is the area of the H section shown here. I'll let you review the calculations at your own pace. The total area was 1093.75 millimeters squared. I will leave you with one further question. The sketch shows an aluminium alloy Z-section extrusion. Given the geometry stated below in the table, we have to calculate the section's area in both millimeters squared and meters squared. Notice for reference, the geometry in the table is stated in centimeters. The symbols shown here and the dimensions shown underneath relate to the symbols shown here in our sketch. The answers are given in the bracket. As the Z section can be considered a compound section, again you need to break it into simpler shapes. This is a quite thought-provoking little question. I would encourage you to stop the presentation and attempt this question now, but on the following slide I will show you a hint to find the area of the Z section. And here's a suggested hint. The top flange is considered to be a rectangle, as is the bottom flange, but the web of the Z section is actually considered to be a parallelogram. You can calculate the base of the parallelogram, labelled B here from geometry, and also calculate the height of the parallelogram, labelled D, again from geometry given. I hope that helps you solve for the answer stated in the question. Here's the bibliography used to help generate this presentation, and I hope this has been of interest to you, and thank you for viewing.